Hello students, good evening all. So welcome back to our sessions. So far we have actually started with the concept of integrals and we have finished the first and second part where we have discussed indefinite integrals first and then we have even discussed the definite integral parts. Right, so coming to our today's session. So today's session will be basically the application part of our integrals. So application part is nothing but majorly it will be dealing with the areas under the curve. So whatever the curves will be given, so based upon that we have to find the area under curve. So there is that's the another name we can say. So which is nothing but our application part of the integrals. Right, so this will be our first session in this application part of integrals. So we'll just quickly have a view on what and all concepts, what and all things we are going to discuss in our today's session of applications of integrals. So we are going to begin with the introduction to it. So basically what are these applications of integrals and all. So as I mentioned, it is something to do with the areas under curve. So that is the application part of our integrals. So we'll just have a quick introduction to it, like how we'll be representing that, what is the quick definition of it. So that and all we are going to cover in our introduction part of the applications of integrals. And the next and very most thing here is curve tracing. So if you guys remember, while learning in our lower sections, if there is a line, you know how to plot the graph of the line. Right. So basically, we can actually get more information when we plot a graph, when we plot the curve, than by looking at the curve itself. Isn't it? So if we could able to plot the curve, we can predict that whether it's a increasing function, whether it's a decreasing function. So in which area, in which typical quadrant exactly those curve lying. So we actually have a lots and lots of information when we actually plot that graph, like when we actually plot the curve on a graph sheet. Isn't it? So you guys learned how to do that. You have typically done with the linear equation in two variables, and you know how to plot that and you know how to find the solution because we have already seen that also. Right. So here the next and most important, because as I mentioned, this application of integrals is nothing but to finding out the areas. Right, so finding out the areas under the curve. So if we want to find the area under the curve, first we should know what is the particular area which we actually required. Which means first thing is we have to actually plot the curve. Right. So that's why we'll be having the curve tracing first. So by looking at the curve itself, like by looking at the graph of the curve, we can actually predict lots of information than a simple equation of the curve, simple expression of the curve. So that's why we'll be seeing the curve tracing first. Like it's easy, like we'll just have few steps, we'll just look over it. Like it's already obvious that you know how to plot it, but there are few more things like what can the additional information we can see by the graph and all. So that we are going to look into here. And after the curve tracing, the next part and the most important, which is nothing but our application part here, is nothing but area bounded by a curve. Right. So area bounded by a curve. So there will be a curve which is given. So with respect to that, we are going to find the area bounded by that respective curve. So it could be with respect to the x-axis and the curve. It could be with respect to the y-axis and the curve. So it can be anything. Right. Or else there can be two different curves and we can actually find the area bounded by those two curves itself also. Right. So it actually depends upon the question which they have mentioned and what are the curves which they have given in the question. Right. So it's basically area bounded by a curve. So how we actually find the area bounded by a curve. Right. So after that we'll just quickly have few things here. That is nothing but we are going to look into what is this symmetrical area. Like we know what is a symmetrical graph and all. So in the same way, you might have already aware of this symmetrical area and all. So we are just gonna look into that, and as well as we are going to look into what is this positive area and what is the negative area. So basically negative area is nothing but when we actually have the area or the curve which we have to find the area is in our fourth quadrant, like it's in our negative side of the axis. So it's like that will become as a negative area, right? But in overall the area won't be negative, but it will be in that negative side of the quadrant, we can say negative side of the coordinate axis, right? So the next will be the positive and negative areas. So these are the typical concepts that we are going to focus and have a look over in today's session of applications of integrals. So along with that, as usual, we'll just do some questions related to it. So for curve tracing, we can do. For area bounded by a curve, we'll be doing. So like that, each of the corresponding concept, we are going to deal and solve the questions related to that concepts, right? So let's quickly start with the definition, like the introduction part of our area under the curve. So basically it is nothing but our application of integrals, right? So as I mentioned, the most important application of integration is nothing but finding the area under a curve, right? So for integrals, we'll be having the most important application that we are going to learn is nothing but finding the area under a curve, right? So now how we actually find the area under any given curve, right? So to find that area under curve, we should be starting with the basic part of it, right? So what is the basic and first and foremost thing we have to do? So in order to find the area, we need to know the basics of plotting a curve, right? So here, if we want to find the area under curve, so the first and foremost thing here, what we have to do? We have to plot the given curve, right? So we should be aware of this basic step, that is plotting a curve, right? And then once we plot the curve, and the next step will be using the integration, then use of the integration with appropriate limits to get the answer, right? So the first and foremost step is nothing but we have to plot the given curve, and then we'll be checking the corresponding appropriate intervals, that is limits, and using that limits we are going to find the integration that will lead us to the answer, which is nothing but the area under the curve. So this entire procedure, so this entire process of finding area of some plane region, if you are doing for some of the region, that will be quadrature. So that is called to be a quadrature, right? So in our application part, we are going to discuss, that is our area under curve, and what are the two steps which we have to follow. The first and basic step will be plotting the curve itself, and then we will be looking for the appropriate limits or our intervals, and using that appropriate limits, we are going to do the integration of our curve, which leads our to get the answer, which is nothing but area under that particular curve, right? So this is the quick intro part for our applications of integrals, which is nothing but the area under the curve. So now, as I mentioned, the first point is nothing but plotting the curve, right? So here that we are going to see here, which is nothing but our curve tracing. So basically curve tracing is nothing but it's a technique which provides a rough idea about the nature as well as the shape of the plane curve, right? So if we are having any of the curve, we know how to plot it. So it's not simply plotting. By looking at the plot of the curve, we can actually predict some of the information regarding that corresponding that particular graph, right? We are going to grasp some of the information from that curve, right? So that we are going to look into here. So what and all typical idea we will be getting from that curve, what is the nature we are going to see, what is the typical shape of it. So those information and all will be coming from the curve tracing here, right? So let's have a look here. Step 1. So can you guys think over it, like how you plot a basic curve if suppose I have given you a linear equation in two variables. You guys know how to plot it, right? In the similar way, here there are few steps which we can follow and we can get the plot of our curve, right? So let's have look over the steps one by one here. So what is the first step here? Check whether the origin lies on the given curve. Right, so the first, so in general, so let's talk in general. So if I have given a curve or a line equation, so what you will be doing? You will be checking whether it's lying on the origin or not, and then you will be checking by substituting x equal to 0, and then you will be checking by y equal to 0. Like, to why we actually do that? To actually plot the curve. Right. So in the same way, here we are starting with the step that is check whether the origin lies on the given curve or not. So that is our first and foremost step. So after that, we have to even check for other points lying on the curve by putting some value. So it can be x equal to 0, it can be x equal to 1, so it can be anything. So let me take an example, x square equal to 2y. So it is a curve, yes or no? So here the given curve is nothing but x square equal to 2y. So here first step what we are going to check? We are going to check whether the origin will be lying here or not. Right. So if my x is 0, then similarly the value of y will also be 0. Yes or no? So on this curve my origin is lying. And how can we get the other points? So we can get any other points by putting some random values of x. So I can take x equal to 0, I can take x equal to 1, I can take x equal to 2. So if I take x equal to 0, what is my y value? That is 0, which is nothing but my origin. If my x is 1, what is my y value? 1 by 2. If my x is 2, then what is my y value? 4 by 2 will be 2. Right, so these are some other points which are actually lying on the curve, which we get by substituting x values, that is x equal to 0, x equal to 1 as well as x equal to 2. So likewise, using these points, we could actually plot the graph. Right. So after that, check whether the curve is increasing or decreasing by finding the derivative of the function, and also check for the boundary points of the curve. So how we will be checking whether the function is an increasing function or decreasing function? So how we'll be checking? We'll be finding the derivative. We have discussed this in our continuity chapter. We are going to find the derivative f dash x. If that is less than 0, then we'll be having an increasing function. If it is greater than 0, then that will be a decreasing function. So to predict whether the given curve is a increasing or decreasing, we actually find the derivative of it. So it actually depends. In some questions, it may not be required. But while tracing the curve, we actually try to get the in and overall information which we could get from that entire curve. Like what and all information we could get. So that will be putting into our tracing of curve. Sometimes it might be required while dealing with our areas of curve. Sometimes it may not be. Right. But you should be aware of the things how we actually get and what and all the things we can get while doing this curve tracing. Right. So in this first step, we'll be just taking some points and we can plot it. And second step, we have to check whether our given curve is increasing or decreasing by finding the derivative. Right. And the next, check whether the curve f of x comma y is 0 is symmetric about x-axis, y-axis or horizon. So if once we could plot the graph, once we could plot the curve, by looking at the plot itself, we can say, okay, whether it's symmetric to about x-axis or whether it's a symmetric about y-axis or else it is symmetric about horizon. So this information also we can get. Right. And the next will be find out the points of intersection of the curve with the x-axis and y-axis. So how we will be getting the point of intersections of the curves? So if for suppose this is my coordinate axis, point of intersection means if suppose I am having this line. So this is point of intersection of this line with y-axis and this is the point of intersection of this line with x-axis. Right. So how you will be getting this point? You will be getting this point by substituting x equal to 0 and we'll be having, sorry, this will be y equal to 0 and we'll be having some x value. Similarly here, x equal to 0 and we'll be having some y value. right? So as usual, you can see for the previous example also we could do that. So if this is my curve x square equal to 2y, if I substitute my x equal to 0, I am having y equal to 0, right? What happens if y is equal to, so this means it's directly intersecting at origin itself, right? So if there is one more curve like something like this, x plus y is equal to 1. So let me take the line x plus y equal to 1. So for this, if my x equal to 0, what will be my y? Y will become 1. If my y equal to 0, what will be my x? My x will become 1. Which means how my graph will be looking like this. So it will be something like this. When x is equal to 1, y will be 0. And when y equal to 1, x will be 0. Right. So these are the 2 point of intersections of the curve with the x-axis as well as the y-axis here. So this can also we can check by while plotting the curve on the coordinate axis itself. Right. And here we are having few more, that is identify the domain of the given function and the region in which the graph can be drawn. So we know how to find the domain. Right. If suppose I am having some 2x, well, you guys have an idea how to find the domain. So domain is nothing but what and all the x values we are taking. So if for the previous also we can check. So this is the graph we are having for the line. So all the x values we can substitute here. So those will become our domain, and what and all values we are getting on the y-axis, those will become our range of the given curve, right? So here for this you can predict and you can identify what is the domain of the given curve. So that's as simple as that. You can see after by looking at the plot itself you can get an idea, or else in general also you can find it, right? And check the behavior of the graphs as x tends to plus infinity and minus infinity. So we can check the graph behavior. So if it is going to plus infinity, how it will be when it going to minus infinity. So for this itself you can see it is going to plus infinity, in the sense it will be going like this, while it will going minus infinity it will be going something like this. So this is how the behavior will be for any graph. So it depends upon the curve. So we can actually predict the behavior also of by looking at the graph, right? So these are the typical things which we can get from our curve tracing. That is nothing but by plotting the graph of a curve, right? So first thing we just plot by taking some random points, and then we'll be checking whether it's increasing or decreasing by finding the derivative, and then we'll be checking the intersection points on the x-axis as well as the y-axis, and then we'll be checking whether it is symmetric about x-axis or symmetric about y-axis or symmetric about the origin. And even we can predict the domain and range of the curve, and then we can look at the behavior of the curve while it's the x value tending to plus infinity as well as the x value tending to minus infinity. So these are the steps that will be coming into picture while we are plotting a graph. So now let's have a quick look. So here you guys have to sketch the given curve, and you can just list down the information you are getting from the curve. By looking at the curve itself you can get some of the information. I am not saying for every curve you have to find whether it's increasing or decreasing. So here my question is to sketch the curve. You can sketch the curve, and by looking at the curve itself what and all information you are getting, you can just list it down. So here you can see the curve which is given. The curve which is given here is x square by 4 plus y square by 9 equal to 1. You might have identified what type of figure it is by looking at the equation. So if anyone plot the graph of it, plot the curve, you can let me know what is the curve, and you can let me know what and all the intersection points on the x-axis, intersection point on the y-axis, because that's easy, right? By looking at the graph itself, we can get that point. So using the first step, you can plot the graph, and you can check whether the origin is lying on this curve or not. And you can check whether it's symmetric about x-axis, y-axis, or horizon, in something like that. And you can tell me the intersection points also here. Come on guys, did anyone got the things? Did anyone plot the graph? I'll just check the comments. Okay, ellipse, exactly. So this is the ellipse. So we can say this curve, first step is nothing but the curve which is given is a ellipse. So this is the information we can get. And what can be the other information you can predict? So we can check according to the steps which we have seen whether the origin will be lying here, lying on the curve or not. Okay, Shivaranjan has already given the intersection points. Exactly, okay. The intersection points on x-axis as well as the y-axis here. So can you tell me whether origin is lying on this curve or not? Any one of you? Because we have to check that in the according to the steps which we have seen our tracing of curve. And can anyone second step whether you have to check whether it is passing through origin or not. And third, someone Shivaranjan has already given the intersection points on the x-axis as well as the y-axis. So if we take the intersection points on the x-axis, so what are the intersection points? So minus 2 comma 0, 1, as well as 2 comma 0 is the other point. And on y-axis, what are the intersection points here? One is 0 comma minus 3 and the other is 0 comma 3. Right. And one more thing we can predict is it is symmetric. So it is symmetric about which axis? So here by looking at the figure we can see so how the figure will be looking here. So it will be something like this, which means here it's a origin, which means our given curve is not passing through origin. So not passing through origin. That is our second point which we can predict. And the fourth and final point, can anyone tell me this graph is symmetric about which axis? So the given plot, the given curve is symmetric about which axis? Come on guys, quickly. I'm just looking for your answer. Anyone? So the curve is, so you can observe if this is our x-axis, it's obviously symmetric about x-axis. As well as if we see with respect to y-axis, the given curve is symmetric about y-axis also. So the given curve x square by 4 plus y square by 9 equal to 1 is symmetric about both the axis x and as well as y. So these are the basic information which we can predict, which we can conclude by plotting the given curve. So it is symmetric about both the axis x as well as y. Right, so this is so it's actually the basic thing which we have to require while finding the area under the curve. So that's why we have started with this sketching the curve or getting the details from plotting the given curve. Right, so let's move on to the next one. So the next one we are having here is area bounded by a curve. Right, so as I mentioned, so the most thing here, that is our application part, that is nothing but area bounded by a curve. So first we are going to see area bounded by a curve with respective to the x-axis. Right, so here we are going to take one curve and we are going to find the area under that curve as well as the x-axis. That means area between the x-axis as well as the given curve. Right, so if for suppose we are having a curve that is y equal to f of x. Right. So the area bound the curve y equal to x-axis. So here we are having a curve y equal to f of x. So bounded by this curve with the x-axis. So in between y equal to f of x as well as the x-axis. So the area between these two we have to find, that is nothing but the area bounded by a curve with x-axis. Right, so how we'll be finding that? Right, so first the area bound by the curve y equal to f of x with the x-axis in between the two limits, that is two odd coordinates here where x equal to a and x equal to b. So these are our intervals. So that is directly given by the formula. Area will be equal to integration of the limits a to b, the given curve y dx. That is nothing but integration of the given curve within the limits a and b. So here the given curve is f of x dx. So it's as simple as that. So we have to pick those limits and then we have to find it. So somebody asking for the symmetry of the previous one. So it is symmetric about both the axes. So both the x-axis as well as the y-axis. You can identify you can observe the figure. Right, so this is our first part and our area bounded by a curve, which is area bounded by a curve with x-axis. So this is the formula which we'll be using to find the area under the curve. Right, so let's see some examples here. So let's start with the examples. So find the area bounded by the curve y equal to f of x. That means my given function here is f of x equal to x cube. So here we have to find the area bounded by this curve with respect to x-axis, and the ordinates are also given here, which are nothing but x equal to 1 and x equal to 2. So can anyone quickly find the answer here? Excuse me. Come on guys, quickly. Just now we have seen what is the formula which we'll be using for area bounded by a curve with x-axis will be integration of the limits a to b f of x dx. And you guys know how to do this integration because it is nothing but simple our definite integration which we have seen. So somebody has given x 7 by 4. So if anyone get the same answer, please let me know. Okay, 15 by 8. Sorry, 15 by 4. Okay. So let's see for 2-3 answers so that we can check whether the answer is correct or not. Come on guys, quickly. So you can see we can simply apply this and substitute our function as well as the given limits. And then we have to do the simple definite integration, which we are already familiar with that. Okay, even Shyam got the same answer, 15 by 4 units. Okay. So let's see for two more. Shivaranjani and Shyam has given the answers. Come on, guys. Others? Okay, even Arun got the same answer, 15 by 4. So let's see how we'll be doing. So here, what are our limits? A to B, that is nothing but 1 and 2. So integration 1 to 2 f of x. So what is our function? X cube. So x cube dx, which will be equal to, so integration of x cube will be x power 4 by 4. And here our limits are from 1 to 2. So this will become 2 power 4 by 4 minus 1 power 4 by 4. So 2 power 4 will be 16 by 4 minus 1 by 4. Right, so this will be LCM for 16 minus 1, 15 by 4 units. So here the area bounded by the curve y equal to x cube as well as the x-axis is given by 15 by 4 units, square units. Right, so this will be the answer, and most of you has got the answer, Lakshmi, Arun, Shyam and Sivaranjani. So let's get into one more question and see how we can do it. So here comes the next question, guys. So here I have simply changed the curve and the rest will be the same as usual. So come on, guys, only the curve has been changed here. So initially our curve is y equal to x cube. So now it has been turned out to be y equal to mx. So what is the area formula which we'll be using? Area equal to integration from limits a to b f of x dx. Okay, Arun has given the answer, guys, 3 by 2m. Okay, so let's see for a few more answers and then we can verify the answer. Okay, Shyam also given the answer, 3m by 2. Okay, so two of you has already solved it. Come on, guys, quickly, others. What about Rachel, Tara? Quickly do it. Okay, even Lakshmi has given the answer. Okay. So the same procedure guys here. So what are our limits? Limits are from 1 to 2 and the function here is mx. So it will be dx. So here m is a constant. So we can pull m out. So it will become integration from 1 to 2 x dx. And what is the integration of function x? That will be x square by 2. And the limits which we are having here is from 1 to 2. So let's take m as a common and we can substitute 2 here. That means 2 square by 2 minus 1 square by 2. That means 4 minus 1, that will be 3. So m into 3 by 2, which is nothing but 3m by 2 here. So the area bounded by the curve y equal to mx as well as the x-axis within the limits x equal to 1 and x equal to 2 is given by area equal to 3m by 2 square units. Right. So these are our basic levels of questions where we are actually finding the area bounded by the curve. So let's move a bit ahead. So let's get into the next one here. So find the area included between the parabola and its lattice rectum, which is at x equal to a. So the first and foremost thing here is you guys have to plot this graph as well as the lattice rectum. So that is the first thing here. You have to plot the curve, that is you have to plot the curve which is given y square equal to 4ax. First quickly plot that guys, and here the area which we have to find should be in between this curve as well as the lattice rectum which is at x is equal to a. Come on guys, quickly plot the graph first. Plot the curve here which is given, which is a parabola. And along with the parabola, you have to draw the lattice rectum also, because now the question is area included between the parabola as well as the lattice rectum. So if you plot the graph, you'll be having the idea what will be your limits which you have to take and what will be the function which we have to integrate. Okay, someone has already given the answer. 8a cube by 3. Is it so? So let's wait so that some others also can get the answer. So plot. Have you guys plotted the graph? So let's see what will be the curve which is look like here for our parabola. So we know how the parabola will be. So my parabola will be something like this, because my parabola will be having the horizon, touching the horizon here, x0 and y0, right? So here we have to draw the lattice rectum at x equal to a. That means, for suppose if x here is a, then what about my y? So y square is equal to, substitute x here, that is 4 into a, which is 4a square. So if y square is 4a square, then y will be equal to 2a, that is plus or minus 2a. So one point will be somewhere here where the coordinates will be a comma 2a, and the other will be in the other quadrant here, that is a comma minus 2a. Right, so now we have to find the area included between this parabola and the lattice rectum, which is this entire area. Right, so this is symmetric about our x-axis or not? So this is symmetric about our axis or not? So here you can see these two parts are symmetric. Right, which means if we could find this area, so let me note down, name it here, A, O, A, B and C. So to get the entire area of OABC, that is nothing but will be equal to 2 times of OAB or 2 times of OCB. Right, so area of OABC, the region, will be equal to 2 times of area of region OAB. Yes or no? So if I take 2 times of it, so what are the limits? So from what and all points my curve will be changing here? From 0 to x is equal to a. Right, that means 0 to a, my curve y here. Right, so this is my curve. So this is varying with respect to my curve, so that will be y, which is equal to 2 times of the limits 0 to a. So what is my y here? So given curve is y square equal to 4ax, then y will be equal to root over 4ax. So now what will be my area bounded by the parabola and its lattice rectum? It's nothing but given by 2 times of the integration of root over 4ax within the limits 0 to a. So let's quickly find this indefinite integration and get the value area bounded here. Okay, Arun Lakshmi has given the answers, 8a square by 3. Okay. So what about others, guys? So now I have given the expression. So quickly integrate this and let me know the final answer. So now you might have understood how to take this limits and all. So here the upper curve will be taking. So this is varying from the x value 0 to a. So those will become our limits. As we are doing the limits from x, our expression which we are taking here, that should also be in terms of x variable. So that's why our function which we are integrating is also in terms of x, that is root over 4ax. Right, and the limits also are our x coordinates which are varying from 0 to a. Right, so quickly find this integration. So here the area will be equal to, the required area will be equal to 2 times of integration within the limit 0 to a root over 4x. That can be written as 2 root ax. And 2 can be pulled out, so it will be 4 integration 0 to a root a and root x. And again root a can also be pulled out because that's also a constant. So it will be 4 root a integration from 0 to a. Root x can be written as 1 by 2 dx. So this will be the integration part which we have to do. So I already got 3 answers. Arun, Lakshmi as well as Sivaranjani has given the answers. 8a square by 3. Okay. So let's simplify it. So we are having 4 root a and integration of this will be 2 by 3 x power 3 by 2 right? So and the limits 0 to a. So let's substitute a here. So 4a power 1 by 2, 2 by 3. If I substitute a here, 3 by 2. So no need to substitute 0 because anyways it will become 0. So now this will be 4 into 2, 8, 8 by 3. So if I add these powers, 1 by 2 plus 3 by 2, that will be 4 by 2, which is a square. Here it will be 1 by 2 plus 3 by 2, which is 4 by 2. So 8 by 3 a square. So the area which is included between the given parabola y square equal to 4ax and its latest rectum at x equal to a is given by 8 by 3 a square units. Right, so this is how we'll be getting the area under the curve when we have the plot, and how we actually do the the limits, how we actually pick from the graph and all. Right, so let's move on to the next one, guys. So far what we have done the area bounded by a curve with respect to x-axis. But now what we are trying to do? We are trying to do the area bounded by a curve with y-axis. Y-axis means now what will be the change? The function which we are going to do the integration, that should be in terms of variable y, as well as the limits also be in terms of y. Right, that will be the difference when we actually doing the area bounded by curve with x-axis and area bounded by curve with y-axis. Right, so let's observe here. So the area bounded by a curve y equal to f of x. So here we can take this instead of y equal to f of x, we can take this x equal to f of y. Right, so with the y-axis between the ordinates y equal to a and y equal to b. So that is given by our area here will be. So when it is with respect to y-axis, our limits should be the y coordinates. So here the y coordinates are given to be a to b, and here the function which we are integrating should also be in terms of variable y, which means f of y dy. So initially that is with respect to the previous one which we have done is with x-axis. So it is in terms of x. So here the limits are x coordinates and the function will also be in variable x. Whereas here we are doing with respect to y-axis. So it will be changing here. Alright, so I hope you guys got the idea how to do with the area bounded by a curve with x-axis as well as y-axis. So that's the only change when we are doing with x-axis, the function should be in terms of variable x. When we are doing with y-axis, the function should be in terms of the variable y. Same way, the limits also should be in x-axis. Those should be the x coordinates. In y-axis, those will be the y coordinates. Right, so let's see some questions related to our area bounded by a curve with respect to the y-axis. So here comes the first question, guys. So quickly, the methodology will be the same thing. There will be a slight difference. So instead of x-axis, here we are going to deal with y-axis. So come on, guys. So you can look at here. Find the area bounded by the curve. So here the curve which is given is x square is equal to y by 4. And the ordinates which is given is y equal to 1 and y equal to 4. So quickly. So what is the thing? What is our formula for this? So area will be equal to integration within the limits a and b, which are our y coordinates. And here the function also should be with respect to the y variable dy. Come on guys, did anyone got the answer? Okay, 7 by 6. Okay, let's see others. So here what are the limits? So limits will be integration from 1 to 4 and our given curve is nothing but x square equal to y by 4, but we have to take x, that means root over y by 2. So here the function will be root y by 2 dy, which is equal to 1 by 2 integration from 1 to 4 y power 1 by 2 dy. So quickly do the integration here. So just now we have done the similar type of integration, x power 1 by 2. Okay, Lakshmi, Sivaranjani, Arun has given the answers, guys. So here this will be 1 by 2 into 2 by 3 y power 3 by 2 and the limits are from 1 to 4. So this will be the expression. So y power 3 by 2 and limits are from 1 to 4. So this and this will be getting cancelled and we'll be having 1 by 3. So 4 power 3 by 2 minus 1 power 3 by 2. So anything power 1 will be 1 only. So 4 power, this will be 2 square. 2 will be getting cancelled, which is 8 here. That means equal to 1 by 3. 8 minus 1, which is 7. Which is equal to 7 by 3. So here for this curve, that is area bounded by the given curve, x square equal to y by 4. Within the lines y equal to 1 and y equal to 4 is given to be area equal to 7 by 3 square units. Right, so I hope you guys got the answer here. So let's move on to the next one, guys. Next question. So here comes the next question. Area bounded by the curve, that is y square equal to 4x. Sorry. Y square equal to 4x. Y axis and the line y equal to 3. So here you have to plot it and then look over it. Then you'll be getting what are the limits you have to take. So come on guys, what is the curve here which is given? The given curve is y square equal to 4x and what are the other lines here given? One is y axis and the other is y equal to 3. So quickly plot the graph, then you will be having the idea what are the limits which we have to take to find the, in order to find the area bounded by this region. Okay, Arun has given the answer. So let's see what about others. What others will give. Once you just check your answer also, Arun. So here what is the area which is given? So we just have to plot the graph first. So y square equal to 4x. So it will be a parabola obviously. So it will be something like this. And y equal to y axis will be this one. Right. And we'll be having y equal to 3. So it will be somewhere here. So let me take y equal to 3 somewhere here. So the region bounded by all these three is nothing but this shaded area or not. So what is this point? Horizon. Right. And what is this point? What is the y-axis here? So y-axis will be 3 and x will be 0 at this point of view. So here we can find y will be 3 and x will be, so here 3 will be 9 by 4. So x will be 9 by 4 here at this point on the curve. But what is the required area which we are having? So the required area is bounded between the curve, this part, and the y-axis, this part, and the line y equal to 3, this part. So this is the entire required area. So as we are doing with respect to y, so my curve will be, so here y square equal to 4x. So my curve will be y square by 4. And what will be the limits? So from here to here, what are my y limits? So it is y equal to 0 to y equal to 3. So y equal to 3. So this will be my integration, which is integration of the curve y square by 4 dy within the limits 0 to 3. So this will be my area, which is the region bounded by the curve y square equal to 4x and the y-axis as well as the given line y equal to 3. So let's simply integrate this and see what will be the area here. Sorry. So it is 0 to 3 y square by 4 dy. So 4 is a constant, so we can pull that out. So integration y square dy and the limits are 0 to 3. So then it will be 1 by 4 y cube by 3 and the limits here are 0 to 3. So it will be 1 by 4 and then 3 cube by 3 minus here it will be anyway 0. So 1 3 will be getting cancelled. Right. So yeah, 1 3 will be getting cancelled. So it will be 3 square by 4, which is 9 by 4 square units. So the area bounded here is nothing but equal to 9 by 4 square units. Yeah, it's 9 by 4. So Shyam and Arun has given the answer perfectly correct. So this is it, guys. So this is how we'll be finding the area bounded by our given curve with respect to the x-axis as well as with respect to the y-axis. And here we are having few more concepts in our finding area under curve. That is, so instead of with respect to x-axis and y-axis, we can have some other curve and we have to find the area bounded by these two curves. So that there are few more concepts. So that we are going to cover in our next session of our applications of integrals. So that's it for today. So if you guys have any questions, any queries, you can let me know in the comment section so that I can reply you. Right. So that's all for today, guys. So rest we'll just cover